Oh, sorry, the light is going out here for some reason.
But can you hear us? Yeah.
Yes. Okay. The light is
oh,
on. Yeah.
just the light. Okay. Okay. No worries. So our next speaker is Vincent, and he's from the University of Leuven, and he will discuss scale-separated AdS3 vacua. So we have the recording. Yes. So please, Vincent, whenever you want, you can start.
Yes. Thank you for the nice introduction. It's my pleasure to talk here. So I've indeed been working on scale-separated AdS3 vacua over the summer. I really liked it a lot. And so the motivation for this talk is really that we love string theory as our favorite theory of quantum gravity, but it works best in 10 dimensions. And so it means that it has extra dimensions that we somehow have to deal with if we want lower dimensional theories. So there are two ways in which we typically deal with those extra dimensions, and that's either by localizing all the physics on branes. So these are the so-called brane worlds, where these branes are embedded into higher dimensional spaces. Another route that is more studied a bit more nowadays are flux compactifications, where you compactify your extra dimensions on a compact manifold, as you all might know. And then you hope actually to be able to make these extra dimensions, this compact manifold, small. That condition to make the extra dimension small is what we often refer to as scale separation. So we want the KK length scale, which is inversely proportional to the KK mass. We want that one to be much, much smaller than the cosmological length scales. So a bit like this picture here. And if we have compactification, we do not only want that condition to be true, but we typically also want full moduli stabilization so that we have a nice phenomenological theory. Now, generically, in many, many string compactifications, this condition is not satisfied. Typically, it's such that the KK scale is actually of the same order of the cosmological length scale. And a very simple example would be Freund-Rubin vacua of type 2 string theory, AdS3 times a sphere. But many, many other compactifications have the same feature here. And that has been a reason for many people to formulate conjectures against scale-separated vacua. And I think the most known one is the strong AdS distance conjecture that has been discussed for a long time in the now since a couple of years. Now, I have been working on so-called, as I said, scale-separated vacua. So it means that there are some counterexamples still to these conjectures that we should study a bit further. And we have a lot of them in type 2b, like we have the KKLT and LVS scenarios, although there has been a lot of work on this. Many people also debate the validity of some of these models. But I today want to focus on the status in type 2a, where moduli can be stabilized with classical ingredients, so only fluxes and D branes and O planes. And scale separation in these kind of models can be achieved in a parametric way. That means that there is typically a flux unit that we can send to infinity and achieve scale separation in that large flux limit. In 4D, these type 2a solutions that we have are so-called DGKT-like solutions. So the first one to consider this were the Wolf, Chirjavets, Castro, and Taylor. And that's already more than 15 years ago. And it's set in massive type 2a on a 6-dimensional Calabi-Yau manifold. And over the more than 15 years, it has been the attention to many, many works. So it's widely studied. And I think that now we have a bit more understanding whether these compactifications do sense or not. Last year, we have also considered the same kind of solutions, but in massless type 2A. There you do not compactify on a 6D Calabi-Yau, but on a nil manifold. And these examples have the advantage to uplift to M theory, where things like singularity or O-plane singularities maybe might be resolved. For the rest of my talk, I will not talk about, I will not go into too much detail about four-dimensional vacua, but I will talk about the 3D case, which has gotten attention since 2 years ago by these people here. And actually, you can see these kind of examples as the 3D analog to DGKT-like solutions. So there it's also set on massive type 2A, but since you compactify on a 3D manifold in type 2A, you have, on 3D, you have a 7-dimensional manifold to compactify on. And this is realized here, not by some kind of Calabi-Yau, but by a G2 manifold. So as I said, these 3D examples are a bit like the 4D DGKT solutions. So both may benefit from a G structure geometry. So in 4D, it's SU3 typically. In 3D, it's a G2 structure manifold. They both have O planes. In 4D, it's O6 planes. In 3D, you have additional O2 planes. So it's minimal SUSY. Scale separation is realized in a parametric way. Although, as I told you before, there is a possibility for massless type 2A solutions and M theory uplifts in 4D, but it turns out that in 3D, it's not possible with those ingredients, which I will show to you later. Also, it has been studied by these people that the would-be CFT dual, their operators would have integer conformal dimensions, at least at 3 level, which is very striking property. But it has also been shown that for the 3D case, this is not the case. So no integer conformal dimensions. And then also in 4D, these people here have shown that these DGKT-like solutions benefit from a discrete symmetry. And they contemplate that discrete symmetry might actually be responsible for this scale separation by actually also extending the AdS distance conjecture to allow for these discrete symmetries. But it has also been shown in this paper here that in 3D, these discrete symmetries do not appear. So there are a lot of interesting similarities, but also a lot of interesting differences. And it would be interesting to exploit these more into the future. Now, these vacua constructed by these people here, they did it in a very standard way. So typically, when you look for a compactification, you collect the kind of fluxes that you want, the sources, specify the geometry, you put everything into your action, you do dimensional reduction, you construct maybe a superpotential out of the potential that you have found, certainly here in the 3D case where you do not have really access to a Kähler potential and superpotential formulation. And then if you want to find supersymmetric vacua, you have to minimize the superpotential in some way. So it's a standard procedure, but for my talk, I want to emphasize that there is a faster way to achieve this, and that is by using bispinor equations. I will later explain precisely what they are. But this technique has the advantage that you just have to specify the G structure that you want to use. So in my case, it would be a G2 structure. I don't have to specify anything more. I just take these bispinor equations, I solve them for this G2 structure, and then at the end, I look which kind of sources are compatible with the solutions I find. And so the benefits, again, for this strategy is that torsion classes really do not have to be specified from the beginning. Here, you can do that, but it would make your computations a lot harder. So that's why the people here considered more like the most simple cases in a certain way. So here you don't have to do that. And dealing with most aspects of the O planes can also be postponed at the very end. There is a minimal properties of the O planes that you only have to consider in the beginning of this whole procedure. So this is the way that I tackled this problem. And I will explain to you now what that really is. So these bispinor equations already have a long history in 4 dimensions by these people here. But more recently, 4 years or so, it has also been considered for the 3D case by these people. And the crux of the story there is that you actually just look at the SUSY variations of type 2, you know, the Gravitino variation and the Di Latino variation that you want to set to 0. And what has been verified by many of these people is that actually solving the supersymmetry variations and also solving the Bianchi identities is equivalent to solving the equations of motion. And that's relatively well, nice to do so, because it means that that actually you have just a simple set of equations that you just have to solve and everything comes out of it. Now, these are just spinor equations. You can make bispinor equations out of them by acting with spinors on the left of these equations. And in my case here, I would be interested in at least compactifications to 3 dimensions. So you split the spinors into a 3D part and a 7D part. And then if you do all of the complicated computations, you construct bispinors with these internal spinors here, the 7-dimensional spinors. So you have an even bispinor and an odd one. And through the Clifford map, these bispinors can be mapped to even and odd polyforms. And in the 7D case, for the 7-dimensional manifold, these bispinors here are related. In the 6-dimensional case, it's not. So for AdS4 vacua, so we don't, well, they're completely, they're not related in this way. The nice thing about these bispinors is that they encode all the 7D metric information. So we don't have to bother too much about the form of the metric. It's something that we can compute later if we're interested in this. So luckily, constructing these bispinor equations is something that we don't have to do anymore. It's already done by these people here. And in the presence of O-planes, if you have orientifold involutions, these are the equations that roll out of that whole procedure. So I refer to this one as the first bispinor equation, this is to the second one, and this is the pairing equation. And these brackets, they are the so-called Mukai pairing. It's just the wedge product where you also include an inversion reversal, sign reversal operator here. So as you can see, I also have these terms with a mu here. These terms are only present when you consider AdS compactifications because mu is related to the AdS length scale. And the fluxes F only appear here, and they are only internal fluxes. So you have dualized the space-time filling parts into internal ones. The upper signs are for type 2A, the lower signs are for type 2B. So these are valid for both of these cases, and that's quite nice, I would say. Now, I haven't told you what these bispinors psi minus and psi plus are. So for G2 compactifications, they look like this. So the odd part is defined by 3 form phi, the volume, and the even part by just constant, and the Hodge dual of that phi. And phi is the left invariant 3 form of G2. And star phi, or psi, is its associated 4 form. And the metric can be completely expressed in terms of these forms. So I was not lying to you before. Now, we don't have to consider necessarily just flat manifolds. We can also introduce intrinsic torsion in our manifold, which results also in curvature on our 7D manifold. And the intrinsic torsion can be represented by these torsion classes here, where you can actually decompose them into irreducible representations of G2. So the one refers to the trivial one, 7 to the fundamental, 27 to the antisymmetric tensor representation, and 14 to the traceless symmetric one. And so you can just use these bispinor expressions, plug them into the equations that I've shown to you before, and just solve for everything. And so if you consider type 2A, it's smeared O2 planes and O6 planes, then something that we typically do, because then the equations become a bit more simple. You can, the warping becomes trivial, and the dilaton also has a trivial profile. And when you do so, this comes out. So it's relatively simple, simply looking. So the Ramond-Ramond fluxes are completely expressed by NS quantities. And what is quite peculiar already is that the bispinor equations impose to you that your G2 structure needs to be closed. In principle, they tell you that there is also this torsion clause W14 that sets F2, but you can easily show that when you include that one, that you need O4 planes to make everything consistent, but actually you cannot wrap O4 planes on 2 cycles, on supersymmetric 2 cycles in such compactifications. So you do not include them because then the solutions would not be supersymmetric. So if you do that, then all torsion clauses become 0. And we have to deal, then we are dealing with a closed and co-closed G2 structure manifold. So that's what people refer to as a manifold with a G2 holonomy. And so this shows that this is required by supersymmetry. And in this sense, it's a generalization of what these people have been considering here. There they just looked at manifolds with G2 holonomy, but were not really including or contemplating about other kinds of torsion. So another important point is that there are no AdS3 vacua in massless type 2A of this sort. And that can be easily seen from from F0, because if you put F0 to 0, then this mu, which was related to the AdS length scale or the cosmological constant, then it's 0. And so yeah, you are dealing with Minkowski vacua. So no AdS3 vacua in massless type 2A for these kind of settings. So if you take all of these equations and you supply them with these Bianchi identities here, you can find solutions relatively easy. This was also done in this paper right here, but I will not go into too much detail about that. I think it's more interesting to see that these solutions are indeed scale separated, because that's what I've claimed to you. And this is because there is actually a scaling symmetry in the game, at least when you allow the O2 charge to cancel against D2 branes, charge from D2 branes. So this is something that we will do so that this thing does not appear in the F6 Bianchi identity. So it means that there is a constraint on the four-form fluxes with respect to H. And when you do so, you find that all of these equations here are invariant under the rescalings of all of these forms by F to some power, where this little f parameterizes the amount of four-form flux you have in your compactification. You see that you also, in the large F limit, that the string coupling goes to 0, and that we have to that we are dealing with large volumes. And the scale separation condition here, LKK squared divided by LADS squared. If you work out what this is by using the volume as your KK scale, or that the KK scale is set by the volume, then you see that indeed this ratio shrinks as F goes to infinity. So we achieve scale separation in a parametric way in the large four-form flux limit. So that's just the same as DGKT in 4 dimensions. In type 2B, you can play the same game. You just change the bispinors, you exchange plus the even ones for the odd ones, and you equivalently get these kind of equations. And the main point here is that you see that we are automatically dealing with co-closed G2 structures here. Oh, because this one is co-closed, but we do have torsion clauses here. And this again is some kind of generalization of this paper here, where they only we're dealing with co-closed G2 structures and not contemplating other kinds of torsion clauses, but SUSY requires it to be co-closed. So what they did is indeed general. Here, there is also a scaling symmetry that you can work out, just as in the type 2A case. But you can show with this scaling symmetry that scale separation of these AdS3 vacua in type 2B are not really possible, at least if you insist on keeping your string coupling small and large volume. And that's quite peculiar to me, because so far, at least I don't know about type 2B vacua with where all the moduli are stabilized with classical ingredients, so without non-perturbative effects, where you can achieve scale separation. So not in 4D, but also not in these 3D examples. And that's quite interesting, I would say. Okay, so now I come to the last part of the talk, and that's about the superpotential. So in 4 dimensions, we all know that we can study compactifications or the low energy effective field theory by just writing down a superpotential, a Kähler potential, and then solving the F-term equations to find supersymmetric solutions. Now in 4D, it has been shown before by Kerber and Martucci that a superpotential and Kähler potential can be completely expressed into the bispinors in 4 dimensions. And so these are a function of the bispinors, the fluxes, but also the dilaton, of course. And they have also shown in that paper that the F-term equations of these super and Kähler potential with the bispinors are completely equivalent to the bispinor equations. And that's, to me, a very nice and remarkable result. I like it very much. And the point of my paper is that similar statements are true in 3 dimensions as well. In 3 dimensions, we don't really have the notion of a real Kähler potential and a holomorphic superpotential, because we don't even have like a complex structure really there. But you can still write the real superpotential P that is appropriate for 3D compactifications as a product of some kind of fictional Kähler potential and fictional superpotential. And I found them to be of this form. So the superpotential here has 2 terms instead of 1, mostly in 4D. Again, the upper signs are for type 2A, the lower signs are for type 2B. Strictly speaking, you should take the warp factor and the dilaton as a constant here, but I've written them out in full just to make contact to the bispinor equations for 3-dimensional compactifications. And these formulas are also compatible with the superpotentials that were found by the original papers from 2020 and 2021. So that's a quite nice match. But I've also shown that these are indeed equivalent to the bispinor equations, at least when you compute the variations. So it's like you're used to if you compute the variations of the superpotential. So on P or W and K, you get the bispinor equations back. I will not bother you with all the detailed calculations. I also simply do not have the time for that. But the gist of the computation is that a dilaton variation gives you the pairing equation, this one. A gauge variation gives you the first bispinor equation, and bispinor variations or geometric variations give you the second bispinor equation. And with this delta I mean that you should actually deform the bispinors in representations of G2. So as I said before, G2 has 4 irreducible representations, namely the fundamental, the trivial, the fundamental, the traceless symmetric, and the antisymmetric representation. And if you do that, you find this, this nice bispinor equation. Okay, so we've come to the end. In this presentation, I've shown that bispinor equations are quite efficient, not only for finding supersymmetric AdS3 vacua with a G2 structure, but they're also very efficient to study its properties and indeed to verify that these are, that at least in the type 2A case, scale separation can be achieved, or at least in a massive case, just as these people have been observing before. I've also shown that to you that AdS3 vacua in massless type 2A of this kind of compactifications cannot be obtained. Scale separation is not possible in type 2B for such compactifications either. And lastly, I've shown to you that the superpotential for these 3D compactifications can also be written in terms of these bispinors, and that its variations are equivalent to the bispinor equations. For the rest, I think it would be very interesting to consider whether this superpotential is also valid for generalized G2 structures, because basically the argument that I gave to you, namely that of these variations, only really applies for variations within the class of G2 structures. So for generalized G2 structures, you would have to do a little bit more work. But I think that T-duality suggests that the superpotential would not change its form, because we know that when you do the integrals, when you just have a scalar function for your superpotential, it does not change functionally in form when you do T-dualities. For the rest, I think it would also be very interesting to see what the domain wall interpretation is of this superpotential, typically because from 4D, we know that there is an intricate relationship between those. But it would also be nice to see what its connection is to the gravitino mass, or verify from the gravitino mass that this is indeed the right superpotential. This is something that these people have done for the heterotic case. So 3D n equals 1 supergravity from heterotic string theory. Furthermore, I've only considered smeared orientifold planes. And I think it would be interesting to look at the O6 plane back reaction when you treat them as local sources. So this is what Emeline Farrakos and Tringas have been doing earlier this year, but they used the Einstein equations and dilaton equations of motion. It would also be interesting to do that in the bispinor language. So something that Marchesano, Palti-Kirant, and Tomasiello did for AdS4 vacua. And of course, these AdS3 vacua, they, through the AdS-CFT correspondence, they should have putative CFT duals. And it would be interesting to validate or invalidate all of these constructions by using CFT arguments. And I think that the discussion about the operator dimensions of the dual CFT are very interesting in that regard, and it would be very interesting to see what comes out of it in the future. And with that, I would like to thank you for listening to this presentation.
Thank you. Thank you, Vincent, for the very nice talk. Let's all use our clap emojis. Do we have some time for questions? Maybe while they find the first question, I can ask something. So you mentioned that it would be interesting, like in your last slide, just the one just before this. You mentioned that you would be interested to redo this back reaction computation for this AdS3 vacua, but using the bispinor language. But would this be like an academic exercise in the sense that you just expect to obtain the same results, or do you have an intuition why you might find something new or some new insight?
Well, the academic exercise would be of course very interesting, but more generally, I would say that it would learn you at least something about generalized G2 structures in string theory. And I think it's not only interesting in this AdS3 case, but it would also be very interesting in M theory, because if you, like I spoke to you before about this AdS4 vacua that we have for massless type 2A, if you uplift those, you also have a 7-dimensional manifold, which also is hopefully to be described in these generalized G2 structures. So in that sense, I think it would be very interesting to do this calculation, because I think this would be easier. But also, I think it would be interesting to do that if you think about instabilities of its non-supersymmetric cousins. So I haven't explained that here, But when you change the sign of some fluxes, just as in DGKT, you have the non-supersymmetric cousins of these solutions. And Marchesano and people in Madrid have been studying instabilities where they needed to use these kind of bispinor techniques. And I think for instabilities here, in this case, it would also be interesting.
Okay, okay. Thank you. Any other question?
I have a question, if that is allowed. But I'm the supervisor of Vincent, so I'm not sure I should ask a question, but I'll do it nonetheless. So in the beginning, I was confused about a statement in the introduction. Okay, you motivated the AdS3 conjecture, which is quite a crazy conjecture probably, but it's very interesting. But you motivated from the Freund-Rubin examples, okay? And then you continue and you give examples which evade it, which are examples with orientifolds. But then you explained there recently was a solution in masses type 2A with orientifolds, which can be lifted to a solution without. But that solution is a Freund-Rubin solution. And so I'm confused with your example. Okay, so it seems there are Freund-Rubin solutions out there which are completely scale separated.
I agree with you. I agree with you on that part. I was more referring to Freund-Rubin type of solutions where you compactify on a sphere.
On a sphere. Okay, thank you. Yeah, then I understand. Yeah.
Okay, good point. Any other question?
I have a short question, if I can ask. So do you have intuition in why there is no scale separation in the type 2B dual? I mean, are there also like intercepting of planes and the background is like the same, or what is the difference?
So yeah, I think it's a very, very interesting question, which I would like to see answered in the near future, at least, like why classical type 2B compactifications do not really support scale separation at all. But in this case, it is, I mean, I haven't showed you the details, but you can work out, you can play the same game. You can find a scaling symmetry exactly as you do for type 2A. But there, at least for homogeneous scalings, you find that if you insist on scale separation, or the scaling symmetry was, sorry, if you insist on large volume, in this case, then you are driven to also strong coupling. And so for this type 2B compactifications, I would be very, I would be careful about how to interpret that. So if you insist on having weak coupling, large volume, then scale separation seems not to be possible. And that's not only true in these 4D examples, in these 3D examples, but also in 4D. For 4D AdS compactifications with SU2 structures and O5 and O7 planes. So yeah, it's something, there is apparently some pattern there, and I would like to understand why that is the case. No.
Okay, thank you.
Okay, great. We are a bit over time, so I think for the questions, I think we should stop here.